The goal of this chapter is to make us better thinkers. And it's hard to teach how to think, but this first one is a type of thinking that you were born with. It's called inductive reasoning. It's looking for patterns. So there's these 3 vocab words that I really want you to focus on today. The word conjecture is an unproven statement based on observations. And like I said, even babies can do this. A young child makes a conjecture that all birds can fly, because that young child has seen a pattern, has observed many birds in his life. He's tried to chase them and they all fly away. So it makes sense that he would conjecture that all birds can fly. Inductive reasoning is the process that he's using. He's finding that pattern and making a conjecture. It's a type of thinking, inductive reasoning, patterns. Counterexample, because sometimes you can prove conjectures wrong, and a counterexample is a specific case for which the conjecture is false. It's not an explanation for why the conjecture is false. It's an actual example, a counterexample. So if you wanted to prove this young child wrong, you wouldn't say, "Oh, honey, not all birds can fly. I know you've seen a lot of birds that can fly, but some birds are too heavy to fly, or their wings just aren't developed enough." You wouldn't be sweetie sweet. You would throw down a counterexample. You'd be like, boom, penguins, prove them wrong with a counterexample. Penguins can't fly. That is a counterexample. We don't go into long explanations. To prove somebody wrong in geometry and logic, a counterexample is the most effective way. Let's practice some of our own inductive reasoning. We see a pattern, we're observing a pattern, and we're going to make a conjecture about what the next shape might look like. Not everybody might make the same conjecture. So if I were doing this, I would think, okay, it's going to be an orange square next, and it's going slanty up, slanty, and not everybody would say the same thing. Would it go back to up? Or do you view these as rotating? Because that's how I look at them. It looks like it's rotating around almost like a clock. So this would be my conjecture for what comes next, using my inductive reasoning. To do this number one, I've got 1, -2, 4, -8, 16. We might describe this pattern in a lot of different ways. Some of you might notice that the numbers are doubling and they're alternating positive and negative. Or some people might describe that differently. Personally, I would say that we are multiplying by -2 each time. That's my conjecture. That's what it looks like is going on to me. And so if that were my conjecture, my next 2 numbers would be 16 times -2 and -32 times -2. And there's my conjecture, my educated guess of what's going to come next based on my observation. This time it's asking me to make a conjecture about the number of line segments needed to draw the next figure. So I wouldn't necessarily need to draw it, but I do need to figure out how many. So let's count. I see 1, 2, 3, 4 to make this first one. I can actually be efficient for this next one and call that a line segment and that a line segment. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. I think I see a pattern, and so my conjecture would be how many line segments to draw the next figure. I would say 9. I could try to draw it, but I'm just going to go with that. Next, I'm going to make and test a conjecture about the product of 2 odd numbers. What does product mean? Product means multiply. So I'm going to think of 2 odd numbers and test those out. See what happens when I multiply odd numbers. So I'll just start thinking of some odd numbers to multiply together. Think of some other odds. I'm going to keep them relatively small so I can figure out the answer. I don't know, do you have a conjecture yet about what all of these products have in common? And I'm just seeing that all of these products are odd numbers, so I might make a conjecture that the product of two odd numbers is always odd. And if anybody could come up with an odd times an odd that would prove me wrong, then that would be a counterexample. Again, I think an odd times an odd always has to be odd, but if you can come up with an odd times an odd that makes an even, then you just proved me wrong. Counterexample. Here's our big chance. We're going to find a counterexample. We're going to disprove this conjecture by providing a counterexample. The sum means to add, the sum of two consecutive, two in a row, two consecutive numbers is greater than the two numbers. So here are a bunch of examples. 5 plus 6, 11 is bigger than both of those. 2 plus 3, 5 is bigger than both of those. 100 plus 101, 201 is bigger than 100, it's bigger than 101. All of these times I can see why somebody would make that conjecture, because always when they added two numbers in a row, they got a number that was bigger than either of those previous numbers. It's a great conjecture, but we can prove it wrong by dropping a counterexample. We're not going to explain. If I were going to be sweetie, I would be, oh, well, I think maybe you weren't thinking about negative numbers. Okay, that is a good description of why this isn't true, but when I want to drop a counterexample, I'm not going to go there. I'm going to go, okay, -7 plus -6. Bam. Done. And why is that a good counterexample? Because it's like, oh yeah, so if I take two numbers in a row, they should add up to be bigger than the other two numbers. -13 is smaller than -7. -13 is smaller than -6. So it's kind of like you're leading them along, right? Like, yeah, a penguin is a bird. Yeah, a penguin is a bird, but bam, can't fly. So a counterexample proves a conjecture wrong by a single example.